so we have done fundamental theorem of calculus where we talked about the definite integrals where if we integrate from a to b of f of x, we will get capital F of b minus capital F of a. What we have not done is we have not done that with an equation where we actually had to integrate because we didn't know those rules. But if we want to integrate something like the integral from 0 to 3, oh, thank you. The integral from 0 to 3 of 4x squared minus 2, then the first thing that we need to do is we need to integrate this just using the power rule like we have done. Typically, you are going to write it using this like intermediate step here where you integrate just like we were the other day. So we would increase our exponent by 1, so that'd give us x to the third, and then we'll divide out front by that new exponent, so we'll get 4/3. And then we'll have minus 2x plus c, and then we put this bracket right here, and we'll put 0 and 3. And we want to go ahead and integrate this fully, so what we're going to do here is the 3 gets plugged into the equation here, so that'll be 4/3 times 3 to the third minus 2 times 3 plus c, and then we'll have to subtract 4/3 times 0 cubed minus 2 times 0 plus c. For the most part, these are going to be calculator inactive problems where you've got to work on your arithmetic a little bit here. So I'm going to do this. I'm going to cancel this 3 with one of the 3's right here. So I'll have 4 times 3 squared, which will be 4 times 9, which will give me 36 right here, minus 6 plus c. And then this is just going to be 0 minus 0, but I will have a c right here. And so that's going to give me 30 plus c minus c, but what is plus c minus c going to do? Just cancel each other out, and we get 30 here. So the area underneath that curve from 0 to 3 would be 30 for that. Now let's talk about this real quick. I put my plus c here. Is the plus c necessary for these problems? Okay? Because right here, if I had left that off, because the c canceled out, right? I had a plus c right here, and I had a plus c right here, but this negative got distributed to that plus c, which made it a negative c, and then they canceled out. Is that going to happen every time? It will. It'll happen every single time. So you can put the c if you want on a definite integral. It's going to work out every time. Make sure they cancel. They should cancel every time. But since the plus c will cancel every time, it is not necessary on definite integrals. And definite integrals are the ones that have the numbers here.
What is
So,
the difference between an integral and an interval? Because it feels like you say them interchangeably.
interval is going to be like an interval where this, like something's increasing or decreasing. So it would be like -3 is less than x less than 5, for that. Integral is the squiggly symbol right here, there. So you should not use the word interval like for these. Well, let me say. I guess I would call this the interval. It's like the piece of the graph that you're looking at. It's like your domain. What you're doing right here, this is the integral. You are integrating the function. Like that. So the interval is just what those limits are. So like the ones you had last night didn't have that. Those would be indefinite, or sometimes called infinite integrals that have infinite answers because of the plus c.
Would that be like just taking f prime of x, and this is like taking f prime of a number? Is that comparable to that?
Yeah, kind of, because this is for a certain piece of the graph. So like what we're looking at here, whenever you are when you're doing a definite integral, is if I had the graph f of x equals 4x squared minus 2, we're looking at this graph right here. If I am doing the integral from 0 to 3, it means that I'm just finding that area underneath the curve for this piece of the graph. So it's like this little tiny negative area here, and this like tall, skinny, positive area here for that, but we don't have to split it or anything. So it's finding that just for that section. Whereas if I don't have it sectioned off, it's talking about the general equation for it. So this is going to be used definitely if they ask for the area under the curve, or if they ask us to do something that would require integration and would have like from t equals 0 to t equals 20 or something like that. In with this section is also going to be our trig integration. So trig integration is a little bit different than the differentiation, because when we take the derivative, we know the derivatives for all of the major sine functions: sine, cosine, tangent, secant, cotangent, cosecant. Those are all ones over here that we should hopefully have memorized. Integration is going to be the opposite of that, but because there is no function where you take the derivative and you just get tangent, we cannot integrate tangent. If they give us the integral of tangent, then we're going to have to do something a lot different here. So basically, if you look, all of these over here are the answers to our derivative problems, right? Because derivatives and integrals are inverses of each other. So if the derivative of sine is cosine, the integral of cosine is sine. Now do notice this right here, they did not want to put any negatives over here in what you were integrating. So if we integrate sine, we will get negative cosine. So it ends up like your sines are backwards for these here. So when you take the derivative of sine, you get cosine. And when you take the derivative of cosine, you get negative sine. The integral of cosine is positive sine. The integral of sine is negative sine. So those signs have kind of flipped there. We cannot integrate tangent. Rather, we're going to be able to integrate secant squared is going to be tangent. Secant x, tangent x is going to be secant. Cosecant squared is going to be negative cotangent. Cosecant x, cotangent x is going to be negative cosecant. Yeah, these kind of go in order from most common, you're going to see them a lot, to probably not, but we better know them just in case. Like sine and cosine, you'll see it very often here. So, integrating these very difficult or pretty simple. It just depends on what you're given. If I look at example 2, I've got sine x over cosine squared x, and that is going to be sort of an issue for us because we don't know any like quotient rule sort of things. So if I look over here, I really want this to be one of these right here. Right now it does not look much like any of those. Does anybody have any ideas?
Can you put cosine, multiply by sine, make it cosine negative?
You could, but I don't think it's going to get you anywhere.
I don't think you spoke English then.
I think that's kind of what Joshua was saying right there. That negative exponent, you could do it, but it's not going to really get you anywhere.
Is there a trig identity for cosine squared x?
There is. It's 1 minus sine squared. I also don't think that's going to get us to where we need to go here. But good ideas, because these are legal moves that you could do.
If you rewrite the sine as obviously 1 over cosecant.
It is 1 over cosecant. Also probably not going to be the most helpful.
I don't this is probably isn't helpful either, but can you do like tangent x and then 1 over secant x?
I think yours is probably the closest right here. So, why are you saying tangent? What?
Because sine x over cosine x is tangent.
Right. So, like, if I take this and I make it sine x over cosine x times, and then I could just put this other 1 over cosine x over here, right? I could do that, and then this would be tangent. And what is 1 over cosine? Secant. And then if I look over there at that other slide, do I have tangent secant? I have secant tangent, which is the same thing, right? So if I integrate that, I'll get secant. So this is going to give us secant of x, and then I will need to evaluate that from 0 to pi. So a little bit of trig identity stuff there. And then to get the final answer for this, we'd have to do secant of pi minus secant of 0. And on that unit circle, here's our pi, here's 0. Coordinates here are 1, 0. Over here, negative 1, 0. And it might even be helpful to think of this as 1 over cosine of pi minus 1 over cosine of 0. So cosine of pi would be negative 1, and cosine of 0 would be 1. So I would have negative 1 minus 1, which would give me negative 2. For what we're doing right now, if you see trig, you should be able to do something to what you see there to get it to be just sine, cosine, secant, tangent, one of those integrals that's listed on that second slide there. Until we learn another substitution piece, we gotta be able to get it to one of those. Okay. Questions there? Okay. Basically, I've just put all the other extra type of functions in here as well. So when we take the derivative of the natural log of x, we get 1 over x. So if we integrate 1 over x, then we should get natural log of x. But notice a couple things here. First of all, we have absolute value bars right here. In this case, that is because you cannot take the natural log of a negative value. So those are necessary for that. Students have a really hard time remembering that this one is natural log. They remember the derivative better, but when you see 1 over x, you do not think natural log. In fact, what I think of when I see 1 over x is I want to do x to the negative 1 power, like that. But this actually can kind of help you remember what it is. Because if I try to do the power rule for this, what do I get when I raise my exponent by 1? 0. And then when I divide out front by that number, I'll have 1 divided by 0. But what is 1 divided by 0? That is undefined. So that doesn't work, right? You just get a mess whenever you do that. So any other negative exponents, the power rule works for. But for negative 1, it's actually natural log. So if we see a problem, like example 3 here, where we've got 2 over x, first of all, we can think about this like this. We can think of it as 2 times 1 over x. That 2 can be like a coefficient that gets pulled out. And then the integral of 1 over x is natural log of x. So we got 2 natural log of the absolute value of x plus c. I actually did not give you a definite interval on this one. A lot because logs are going to be like calculator type of problems for that. Okay. 4 is an interesting problem. It is a lot like the problem that we did from the homework, where we had that division. What should we do for this? You do the triple love connection here. You can divide everything by x squared. And so if you do that, we've got 3x squared over x squared plus 5x over x squared minus 2 over x squared. And so if we simplify that, we just have a 3 plus 5 over x minus 2 over x squared. Part of this is not natural log stuff. So when I take the integral of 3, I just get 3x. But when I try to integrate 5 over x, I can't do that using the power rule. If I try, I'm going to get, excuse me, like a 5 divided by 0. So that is going to be 5 natural log, absolute value of x. Now, the last part, this can be written as negative 2x to the negative 2 power. That one is not a natural log. It's only if it's to the negative 1 power. So here you just increase your exponent by 1. So you got x to the negative 1. Divide out front by that negative 1. It will give you a positive 2. And then we would put a plus c on this one because it's not a definite interval. So sometimes those natural logs can be like snuck into a problem that looks like it has nothing to do with a natural log. Questions? All right, let's keep moving. Exponentials are the easiest thing to take the derivative or integral of anything, because the derivative of e to the x is e to the x. So what's the integral of e to the x going to be? Also e to the x plus c. So when you see something like we've got here, where we're integrating, we got e to the x divided by 5, but we can think of that. Now what is happening here? Okay, there we go. My pen was right, like way below where it was supposed to. You can like pull the 1/5 out, and then when you would be integrating just e to the x dx from -2 to 3. So when you integrate e to the x, you just get e to the x. It is itself, but you would evaluate this from -2 to 3. And so that would look like this: 1/5. I'd get e to the 3rd minus e to the -2. You do not need the plus c on that because it's a definite integral. The c's would have canceled out if we used it. And they may simplify those e's in some fashion, but I'm just going to leave them. Okay. Any questions there? I believe this is our last one here. If we are integrating 3 cosine x, the integral of cosine, what is it? Is sine, so we will get 3 sine x. And we've got minus 5e to the x. The integral of that is just minus 5e to the x. And then we would be evaluating that from 0 to pi over 2. And so it would look like this. We would have 3 sine of pi over 2 minus 5e to the pi over 2 minus 3 sine 0 minus 5e to the 0. And unit circle, sine of pi over 2, this is the coordinates 0, 1. Sine is your y coordinate, we'll get 1. So we'll have 3 times 1. And there's not really anything you can do with that 5e to the pi over 2. You're just going to have to leave it like it is. We're going to get sine of 0. Sine of 0 on that unit circle. That's your y coordinate. You're going to get 0 there. And e to the 0, what is it? It is just 1. So we get 5 right there. So we've got 3 minus 5e to the pi over 2. This is going to be plus 5 right here. So we could combine the 3 and the 5. So 8 minus 5e to the pi over 2. And that would be our answer there. Questions? Okay, so that is it. We've got a little bit of time for you to work on your assignment. It is 5 through 29 odd, 37, 47, 48. Hopefully, like last night's homework, it is quite a few problems, but it should go pretty